The impossible machine. In the frozen forests outside Bastogne, in December 1944, a column of American half-tracks rumbled through knee-deep snow, their tracked rear sections gripping terrain that would have stopped any wheeled vehicle dead. The lead vehicle mounted a 75mm cannon, artillery firepower that belonged on a towed gun carriage. The second carried a squad of infantry in its open bay, ready to dismount and fight. The third towed an anti-tank gun while its machine gunner scanned the tree line for German infantry. These weren't three different vehicles designed for three different missions. They were variants of the same basic chassis, a revolutionary hybrid that military engineers had somehow convinced to perform duties that should have required entirely separate vehicle types. The half-track represents one of the most audacious compromises in military engineering history. It was asked to do the impossible: combine the speed and efficiency of wheeled vehicles with the cross-country mobility of tracked vehicles, all while serving as a tank destroyer, personnel carrier, artillery platform, ambulance, command post, and anti-aircraft gun mount. According to R.P. Honeycutt's comprehensive half-track, A Chronicle of American Military Vehicles, American engineers produced over 41,000 half-tracks between 1940 and 1944, creating more than 70 distinct variants from the basic M2 and M3 chassis. The German Sd.Kfz.251, as documented by Hilary Louis Doyle and Tom Jentz in their authoritative Panzertracks series, spawned at least 23 major variants and countless field modifications. These vehicles shouldn't have worked. They were too light to be proper tanks, too slow to be effective trucks, and too mobile to serve as stable artillery platforms. Yet they became indispensable to American, German, and Soviet forces, serving in every theater of World War II, and continuing in frontline service well into the 1960s. The story of how engineers designed these mechanical chimeras reveals fundamental truths about military innovation, compromise, and the unexpected ways that imperfect solutions sometimes prove more valuable than purpose-built perfection. Part 1. The problem that required a hybrid. The mechanization dilemma. The problem began in the trenches of World War I. Military planners watched infantry advance at the same 3 miles per hour walking pace that Roman legions had maintained 2,000 years earlier, while tanks, the great breakthrough weapon, crawled forward at barely 4 miles per hour. The theoretical solution seemed obvious: put the infantry inside armored vehicles that could keep pace with tanks. The practical challenges, however, proved enormously complex. Tracked vehicles offered unmatched cross-country mobility. The continuous track distributed a vehicle's weight across a large surface area, reducing ground pressure and enabling movement across mud, sand, and snow that would bog down wheeled vehicles. But tracks came with crippling disadvantages. They were mechanically complex, requiring constant maintenance. They consumed prodigious amounts of fuel. Most critically, they were agonizingly slow on roads. A tracked vehicle's top speed rarely exceeded 25 miles per hour, and the ride quality was so brutal that crews arrived at battle exhausted and bruised. Wheeled vehicles presented the opposite problem. On roads, trucks were fast, efficient, and required relatively little maintenance. A standard military truck could cruise at 45 miles per hour on paved roads and travel 300 miles on a single tank of fuel. But the moment they left improved roads, their mobility collapsed. Stephen J. Zaloga's M3 Infantry Half-Track 1940-73 describes how wheeled trucks attempting to follow tanks across North African wadis routinely became stuck, stranding infantry far behind the armored spearhead they were supposed to support. The doctrinal problem was equally vexing. The U.S. Army's FM 17-42 Armored Infantry Battalion, published in 1944, outlined a tactical concept that required mechanized infantry to perform contradictory missions. They needed to move rapidly along roads to exploit breakthroughs, a mission favoring wheeled vehicles. They needed to keep pace with tanks across broken terrain, requiring tracked mobility. They needed to suppress enemy positions with mounted weapons while moving, demanding a stable weapons platform. And they needed to transport infantry who could dismount and fight, requiring space and protection that conflicted with weapon mounts. Early attempts and failures. The first attempts to solve this problem were conceptually simple but practically disastrous. Some nations simply mounted armor on trucks. The French automitrailleuse armored cars of the 1920s offered speed and firepower, but became immobilized the moment they encountered soft ground or obstacles. The British experimented with fully tracked carriers like the Universal Carrier, which solved the mobility problem, but was so slow and fuel-hungry that it couldn't keep pace with motorized columns during road marches. The Soviet Union attempted a different approach with the BTR-40 and similar wheeled armored personnel carriers. These worked adequately in the relatively open terrain of the Central Asian steppes, but proved nearly useless in the forested, swampy terrain of Eastern Europe. According to Soviet Lend-Lease records published in Tanks and Armored Vehicles of the USSR 1917-1945, Soviet commanders frequently requested American half-tracks, specifically because wheeled vehicles couldn't navigate the terrain during the spring Rasputitsa, when melting snow turned roads into impassable mud. The Wehrmacht's combined arms doctrine, which emphasized tight coordination between armor and infantry, couldn't function with this mobility gap. Part 2. The Revolutionary Compromise. The French Innovation. The solution emerged, improbably, from French agricultural engineering. In the 1920s, the Sd.Kfz.251 company developed half-track conversions for trucks operating in colonial territories. These vehicles used conventional wheels at the front for steering and a tracked bogie system at the rear for traction. Adolphe Kegres, a French engineer who had worked for the Tsar's motor pool, developed a flexible rubber and canvas track that was far more durable than the metal tracks used on tanks. The genius of the half-track layout lay in its division of labor. The front wheels, directly connected to the steering wheel through a conventional automotive steering system, provided simple, intuitive control. The driver steered exactly as he would in a truck, no complicated clutch and brake steering systems required. The rear tracks provided traction and weight distribution. This arrangement meant that roughly two-thirds of the vehicle's weight rested on the tracks, dramatically reducing ground pressure compared to wheels, while avoiding the mechanical complexity of an all-tracked vehicle. Honeycutt's Chronicle reveals that American military observers first encountered Kegres half-tracks during French military demonstrations in the 1930s. The U.S. Army Ordnance Department immediately recognized their potential, but faced a fundamental problem. The Kegres design was optimized for agricultural and exploration vehicles, not combat operations. The rubber and canvas tracks, while adequate for civilian use, were too fragile for military applications. The suspension system couldn't handle the weight of armor and weapons. The powertrain wasn't designed for the sustained high-speed operation military doctrine required. American engineering, building the M2 and M3. The challenge of creating a military half-track fell to engineers at White Motor Company, Autocar, and Diamond T. Their task was to take the basic half-track concept and transform it into a combat vehicle that could perform multiple contradictory missions. The specifications they received were dauntingly broad. The vehicle needed to carry a rifle squad of 12 men, mount machine guns for self-defense, tow artillery pieces, traverse mud and sand that stopped trucks, maintain 45 miles per hour on roads, and be maintainable by minimally trained mechanics in field conditions. The engineering solution centered on the M3 chassis, which Honeycutt describes in exhaustive detail.
The vehicle measured approximately 20 feet long, 7 feet wide, and 7.5 feet tall. Dimensions carefully calculated to split the difference between conflicting requirements. It needed to be narrow enough to navigate European roads and forest trails, but wide enough for stability when firing mounted weapons. It needed to be long enough to accommodate a full infantry squad, but short enough to maintain maneuverability in urban terrain. The suspension system represented the most innovative engineering. The rear bogie system used vertical volute springs, heavy coil springs mounted vertically rather than horizontally. This design, derived from tank engineering, provided both suspension travel and lateral stability. Each track assembly consisted of 4 road wheels arranged in a bogie system, with the rearmost wheel positioned slightly higher to help prevent track shedding. The entire track assembly could articulate vertically through more than 12 inches of travel, allowing the half-track to absorb impacts that would have destroyed a truck's suspension. Track design proved particularly challenging. The Congress rubber and canvas tracks were too fragile, but conventional metal tank tracks were too heavy and created excessive vibration at road speeds. American engineers developed a hybrid solution, a track made of rubber-impregnated fabric with embedded steel cable for tensile strength and metal cleats for traction. Aberdeen Proving Ground technical reports from 1941 to 1942 reveal that engineers tested dozens of track designs, measuring wear rates, traction characteristics, and failure modes across thousands of miles of testing in conditions ranging from Arizona desert to Minnesota winter. The powertrain presented its own challenges. The M3 used a white 160AX inline 6-cylinder engine producing 147 horsepower, adequate but not generous for a vehicle that, fully loaded, could weigh over 9 tons. The engine was essentially a heavy-duty truck motor, chosen for reliability and ease of maintenance, rather than raw power. This power-to-weight ratio of roughly 16 horsepower per ton put the half-track firmly in the middle ground between trucks, which might have 20 horsepower per ton, and tanks, which rarely exceeded 12 horsepower per ton. The transmission was a 4-speed manual gearbox with a 2-speed transfer case, providing 8 forward gears and 2 reverse gears. This proliferation of gear ratios was essential because the half-track needed to operate across an enormous range of conditions. Low-range first gear could pull the vehicle through deep mud at walking pace. High-range fourth gear enabled sustained cruising at 40 miles per hour on improved roads. The transfer case also included a front-wheel disconnect. At high speeds on roads, the front wheels could be disconnected from the drivetrain to reduce wear and improve fuel economy.
German engineering, the Sd.Kfz.251. While American engineers were developing their half-track, German designers at Hanomag took a different approach with the Sd.Kfz.251. Doyle and Jentz's Panzer Trax No. 15-1 provides extraordinary detail on this vehicle's development. The German design philosophy emphasized protection and automotive sophistication over simplicity and ease of manufacture. The Sd.Kfz.251 used the chassis and running gear of the Sd.Kfz.11 artillery tractor, which had already proven its worth in Wehrmacht service. This common chassis approach had significant advantages: parts commonality, established manufacturing infrastructure, and proven reliability. However, it also imposed constraints. The Sd.Kfz.11 chassis was designed for towing, not for carrying loads or serving as a weapons platform. German engineers addressed this by completely redesigning the hull. Where the American M3 used relatively flat armor plates bolted to a structural frame, a design optimized for manufacturing simplicity, the Sd.Kfz.251 employed interlocking angled armor plates that provided better ballistic protection within weight constraints. The hull sides sloped outward at the bottom, dramatically improving stability and reducing ground pressure.
This design was more protective and more stable, but also far more complex to manufacture. Each Sd.Kfz.251 required approximately 2,500 man-hours to produce, compared to roughly 1,000 man-hours for an M3. The German track system was more sophisticated than its American counterpart. It used a design derived from Panzertank technology, with individually sprung road wheels and a more complex tensioning system. This provided superior ride quality and reduced crew fatigue during long road marches. The tracks themselves were metal with rubber pads, more durable than American rubber-impregnated tracks, but also heavier and louder. The Sd.Kfz.251's engine was a Maybach HL42 TUKRM, 6-cylinder gasoline engine producing 100 horsepower. This significantly lower power output compared to the American M3 reflected different design priorities. German doctrine emphasized protection and load-carrying capacity over speed. The Sd.Kfz.251 could carry 12 infantrymen in reasonably protected conditions, whereas the M3's armor was minimal and its passenger compartment was open-topped. Part 3. Engineering for multiple missions. The personnel carrier mission. The baseline mission, transporting infantry, presented engineering challenges that weren't immediately obvious. Infantry needed to be protected during movement, but able to dismount rapidly when combat began. They needed to see potential threats while remaining concealed themselves. They needed to bring their weapons and equipment, but not be so cramped that they arrived at battle exhausted. The M3's passenger compartment was a masterpiece of compromise. The bench seats folded up against the hull sides, providing more space for cargo when infantry wasn't being carried. The rear door dropped down to form a ramp, enabling rapid dismount. Honeycutt notes that extensive testing at Fort Benning demonstrated that a full infantry squad could dismount and deploy in under 15 seconds. Fast enough to respond to ambush, but not so frantic that men injured themselves or left equipment behind. Protection was minimal by tank standards, but revolutionary for infantry. The hull provided protection against small arms fire and shell splinters, enough to dramatically improve survival compared to unprotected trucks, but insufficient against heavy machine guns or direct artillery hits. This level of protection represented a calculated engineering decision. Heavier armor would have reduced mobility and increased weight to the point where the vehicle couldn't perform its other missions. The armor that was present, typically quarter-inch to half-inch steel plate, was angled to maximize protection within weight constraints.
The weapons platform mission. Converting a personnel carrier into a weapons platform required solving problems of stability, recoil absorption, and ammunition storage that personnel carriers weren't designed to handle. Aberdeen Proving Ground technical reports from 1941 to 1942 reveal the enormous engineering effort required to mount weapons on the M3 chassis. The most ambitious conversion was the M3 gun motor carriage, GMC, which mounted a 75mm M1897A4 field gun, a weapon designed to be towed and fired from a stable, dug-in position. The engineering challenges were formidable. The gun weighed approximately 2,800 pounds and generated recoil forces exceeding 10,000 pounds. The M3 chassis, designed to carry infantry, had to absorb these forces without overturning, breaking apart, or shifting positions so dramatically that follow-up shots became impossible. Engineers addressed this through multiple modifications. The front armor was removed to reduce weight and shift the center of gravity rearward. A substantial steel baseplate was welded to the chassis floor, spreading recoil forces across the entire vehicle structure rather than concentrating them at mounting points. The suspension was reinforced with additional springs and shock absorbers. Most ingeniously, a large spade, a steel blade that could be lowered to dig into the ground, was mounted at the rear. When the gun fired, this spade prevented the vehicle from being pushed backward by recoil. Testing revealed unexpected problems. The 75mm gun's muzzle blast was so intense that it damaged the vehicle's own windshield and instruments. Engineers added blast deflectors and required crews to lower the windshield before firing. The muzzle flash at night was so bright that it temporarily blinded the crew. a problem that couldn't be fully solved but was mitigated by training crews to close their eyes during firing. The M12 GMC represented an even more ambitious weapons platform. It mounted the 155mm M1917A1 howitzer, a First World War-era artillery piece that fired a 95-pound shell over 11 miles. This weapon was never intended to be vehicle-mounted. Its recoil generated forces exceeding 25,000 pounds, enough to flip a half-track completely over if not properly managed. Aberdeen Proving Ground reports detail the extraordinary measures required to make this work. The M12 was essentially rebuilt from the ground up. The passenger compartment was completely removed and replaced with a massive steel structure that distributed forces throughout the chassis. The spade at the rear was enlarged to a huge blade that, when lowered, effectively made the vehicle part of the ground itself. Outriggers extended from the sides, preventing rollover during firing. The result was barely recognizable as a half-track. It was more accurately described as a 155mm howitzer that happened to be mounted on a half-track chassis. German engineers faced similar challenges with the Sd.Kfz.251. Doyle and Jentz document more than 23 major variants, each requiring specific engineering solutions. The Sd.Kfz.251-9 Stummel mounted a 75mm low-velocity gun intended for close support. Unlike American conversions, which often removed armor to compensate for added weapon weight, German engineers maintained protection levels by using more sophisticated weight management. The gun shield was integrated into the whole design, providing protection without adding excessive weight. The mounting system used a combination of coil springs and hydraulic buffers to absorb recoil. The Sd.Kfz.251-21 mounted triple MG-1520 autocannons for anti-aircraft defense, a conversion that presented unique challenges. The guns had a high rate of fire, approximately 700 rounds per minute per barrel, generating continuous recoil forces rather than the single sharp impulse of a field gun. Engineers mounted the weapon system on a complex pivot system that allowed 360-degree traverse and high elevation angles. The mounting had to absorb continuous vibration without failing while allowing the gunner to track fast-moving aircraft. Counterweights balanced the weapon system, preventing it from tipping the vehicle during high-angle firing.
The artillery towing mission. Even as half-tracks were being converted into self-propelled artillery, they continued serving their original mission of towing conventional artillery pieces. This mission imposed its own engineering requirements that often conflicted with the vehicle's other roles. Towing heavy artillery required enormous pulling power at low speeds, precisely the opposite of the high-speed road performance needed for mechanized infantry operations. The M3's transmission, with its 8 forward gears, addressed this through sheer versatility. The lowest gear ratio provided enough mechanical advantage to tow guns weighing several tons through mud and upslopes. Honeycutt notes that the M3 could tow the 155mm Long Tom field gun, which, with its limber, weighed approximately 14 tons, nearly twice the half-track's own weight. The engineering challenge extended beyond raw pulling power. When towing artillery, the half-track's handling characteristics changed dramatically. The towed weight, positioned behind the rear axle, reduced front-wheel traction and made steering heavier and less responsive. The combination of vehicle and towed bun might stretch over 40 feet, requiring much wider turning radii and making maneuvering in confined spaces difficult or impossible. Engineers addressed this through careful weight distribution and the addition of towing equipment designed to manage these forces. The M3 featured a reinforced rear frame with multiple towing points. A pintle hook provided the connection point for the artillery piece's lunette. The hook was mounted on a substantial crossmember that distributed towing forces across the entire rear frame structure. For very heavy loads, additional chains or cables could be connected to frame mounting points, spreading the load even further. The braking system presented particular challenges. A half-track towing several tons of artillery down a mountain road faced the very real possibility of the towed gun pushing the vehicle forward, causing loss of control. Larger artillery pieces therefore included their own braking systems, operated by a crew member seated on the gun limber. Coordination between the half-track driver and the artillery crew became critical, a human factors challenge as much as an engineering one.
The command post and support roles. Many half-tracks were converted to specialized roles that required interior volume and stable platforms rather than mobility or firepower. The M3A1 command post variant removed seats and added map boards, radios, and additional communications equipment. This conversion seems simple, but required careful electrical system redesign. Radio equipment of the 1940s consumed significant electrical power. The M3's standard electrical system, adequate for lighting and engine ignition, was insufficient for high-power radio transmitters. Engineers upgraded the electrical system with higher capacity generators and additional batteries. The challenge was finding space for this equipment while maintaining the vehicle's center of gravity. Batteries are exceptionally heavy. The additional batteries required for radio equipment might weigh several hundred pounds. Positioned incorrectly, this weight could make the vehicle unstable or bottom-heavy. Engineers typically mounted batteries low and toward the center of the vehicle, maintaining stability while providing the electrical capacity command requirements demanded. Ambulance variants faced different challenges. They needed to transport wounded soldiers in conditions that minimized additional trauma. The standard M3's ride quality was acceptable for healthy infantry but potentially dangerous for wounded men. Engineers added additional suspension damping and softer springs, trading some load-carrying capacity and handling sharpness for a smoother ride. The interior was reconfigured with stretcher racks that isolated wounded soldiers from the vehicle's movements through additional suspension systems, essentially providing double suspension, with the vehicle suspension isolating the chassis from ground impacts and the stretcher suspension isolating patients from chassis movements. German variants addressed similar missions with characteristically different approaches. The Sd.Kfz.251/3 command vehicle featured a much more elaborate radio fit than American equivalents. German radio equipment of the period was generally more sophisticated but also more temperamental than American designs. This required additional measures to isolate equipment from vibration and provide stable electrical power. German engineers installed voltage regulators and filters to provide clean power to sensitive radio equipment, systems that American designs often omitted in favor of simpler, more robust equipment that tolerated electrical variations. Part 4. Combat Testing and Doctrinal Evolution. North Africa. Lessons in Desert Warfare. The half-track's first major combat test came in North Africa, where American forces faced German and Italian armies across terrain that ranged from hard-packed desert to deep sand. After-action reports from the U.S. 1st Armored Division reveal how combat exposed both the strengths and weaknesses of half-track design. The positive reports were striking. Half-tracks demonstrated mobility that surprised commanders on both sides. In the Battle of Kasserine Pass in February 1943, American M3s navigated terrain that stopped both wheeled trucks and many light tanks. The combination of front wheels and rear tracks proved ideal for the hard-packed desert surfaces common in Tunisia. The tracks provided traction when crossing wadis, dry riverbeds, and negotiating rocky terrain, while the front wheels allowed higher road speeds than fully tracked vehicles during the rapid movements that characterized desert warfare. However, the North African campaign also exposed serious vulnerabilities. The M3's open top, acceptable in European conditions, became a liability under the intense North African sun. Crews suffered from heat exhaustion, and equipment failures increased as temperatures inside the vehicle regularly exceeded 120 degrees Fahrenheit.
Zaloga's study notes that maintenance intervals had to be dramatically shortened because oil and lubricants degraded far more rapidly than in temperate climates. Dust proved to be a severe problem. The M3's air intake systems, designed for European conditions, couldn't filter the fine North African dust. Engines wore rapidly as dust particles entered cylinders and acted as an abrasive between moving parts. Field modifications became necessary. Units added additional oil bath air filters, increased oil change frequency, and in some cases fabricated dust shields from local materials. The Kasserine Pass battle in particular demonstrated the half-track's limitations as a fighting vehicle. American forces, facing the experienced German Afrika Korps for the first time, attempted to use M3s in frontal assaults against prepared positions. The results were catastrophic. The half-track's armor, sufficient to stop rifle rounds and shell fragments, offered no protection against German anti-tank weapons. The 37mm and 50mm anti-tank guns that equipped German infantry units could penetrate M3 armor at ranges exceeding 1,000 yards. Half-tracks advancing across open desert presented ideal targets and were destroyed in large numbers. This combat experience forced a rapid doctrinal evolution. Field Manual FM 1742, published in 1944, incorporated hard-won lessons from North Africa. The manual emphasized that half-tracks were not armored fighting vehicles and should never be employed as such. Instead, they were to be used as battle taxis, transporting infantry to within a few hundred yards of objectives where the infantry would dismount and continue on foot. The half-track's weapons were for self-defense and suppression, not for engaging hardened targets.
Eastern Front, the German experience. German experience with the Sd.Kfz.251 on the Eastern Front proved even more harrowing. Bundesarchiv military records document how Soviet conditions pushed the German half-track design to, and sometimes beyond, its limits. The first winter of the Eastern Front campaign, 1941 to 1942, revealed fundamental design flaws in the Sd.Kfz.251. The vehicle's sophisticated suspension system, which provided excellent ride quality in temperate conditions, proved vulnerable to extreme cold. Lubricants thickened, seals hardened and cracked, and the complex track tensioning system frequently froze solid. Bundesarchiv records indicate that mechanical readiness rates for Sd.Kfz.251 units dropped below 50% during the coldest weeks of that winter, a catastrophic failure rate. German engineers responded with winter modification kits that included cold-weather lubricants, insulated engine compartments, and simplified track tensioning systems that could be maintained in field conditions. These modifications improved reliability, but never fully solved the fundamental problem. The Sd.Kfz.251 was too sophisticated and mechanically complex for the extreme conditions of the Eastern Front. Soviet responses to German half-tracks were instructive. Red Army anti-tank doctrine specifically addressed half-tracks, classifying them as soft-skinned vehicles, equivalent to trucks, rather than armored vehicles. Soviet anti-tank rifles, weapons that were marginally effective against German tanks, proved devastating against half-tracks. The PTRD and PTRS 14.5mm anti-tank rifles could penetrate Sd.Kfz.251 armor at ranges exceeding 500 yards. Soviet infantry units equipped with these weapons targeted half-tracks preferentially, recognizing that destroying them stranded German infantry far from their supporting armor. The combination of mechanical unreliability and vulnerability to Soviet anti-tank weapons led to doctrinal changes in German employment of half-tracks. By 1943, German formations increasingly reserved half-tracks for specific missions where their unique capabilities justified the risks. They were used extensively for armored reconnaissance, where their combination of mobility and firepower proved valuable. They served as command vehicles,
where protection against small arms and shell fragments was adequate and where mobility was critical. They continued as ammunition carriers and resupply vehicles, roles where their cross-country capability was essential. The Pacific Theater, environmental extremes. The Pacific Theater presented environmental challenges that neither European nor North African combat had prepared engineers for. The combination of tropical heat, extreme humidity, and jungle terrain tested half-track designs in ways their creators never anticipated. American forces discovered that half-tracks performed poorly in Pacific jungle warfare. The vehicles were too large for jungle trails, too noisy for approach maneuvers, and too vulnerable to ambush in the confined terrain. Most critically, the rubber-impregnated tracks that had proven durable in Europe and North Africa rotted rapidly in tropical conditions. The combination of constant moisture and tropical heat caused the rubber to degrade, with track life sometimes falling to under 500 miles, a fraction of the 3,000-mile life expectancy in temperate climates. Maintenance became a nightmare. Unit reports describe how the fine volcanic sand of Pacific Islands infiltrated every mechanical system. This sand was far more abrasive than North African desert dust, causing accelerated wear in engines, transmissions, and suspension components. Salt air corroded electrical systems. Tropical fungi actually grew on wiring insulation, causing short circuits and electrical failures. These problems led to a general conclusion that half-tracks were unsuitable for Pacific jungle warfare. By 1944, American forces in the Pacific Theater increasingly relied on tracked LVT, or landing vehicle tracked, amphibians for assault operations and conventional trucks for logistics. Half-tracks continued to serve in headquarters units and in the relatively open terrain of the Philippines, but they never played the central role in Pacific operations that they held in European warfare.
Korea, the last hurrah. The Korean War, 1950–1953, provided the final combat proving ground for World War II-era half-tracks. U.S. Army Ordnance reports from this period offer fascinating insights into how the design had aged. American M3s, pulled from storage or reconditioned from surplus stocks, initially performed their missions adequately. The Korean terrain, mountainous with poor roads, seemed ideally suited to the half-track's unique capabilities. However, combat experience revealed that the design was dated. North Korean and Chinese forces were equipped with more modern anti-tank weapons, including the B-10 82mm recoilless rifle and various anti-tank rockets. These weapons could destroy M3s at ranges where the half-track's machine guns couldn't effectively respond. The most revealing assessment came from maintenance reports. The M3's mechanical systems, now a decade old in design, required far more maintenance than newer vehicles. The vertical volute suspension, innovative in 1940, was now recognized as maintenance-intensive. The rubber-impregnated tracks, adequate for World War II's relatively short combat lifespans, wore out rapidly in sustained operations. Most critically, spare parts were becoming scarce. Manufacturing had ended in 1944, and the supply system was no longer optimized for supporting these vehicles. Korean War experience accelerated the American military's transition to fully tracked armored personnel carriers. The M75 and later M113 represented a fundamental shift in doctrine. These vehicles abandoned the half-track compromise in favor of full-tracked mobility, aluminum armor for improved protection at reduced weight, and amphibious capability. The lessons learned from half-track employment, particularly the need to protect infantry from small arms fire and the importance of mobility across broken terrain, informed these new designs. Part 5. The Engineering Legacy. What worked? Validating the compromise. Despite its eventual obsolescence, the half-track concept proved remarkably successful within its specific historical context. The design validated several engineering principles that continued to influence military vehicle development. The most important validation was of role versatility. The ability to create multiple variants from a single chassis proved operationally and economically valuable. Honeycutt's comprehensive chronicle documents over 70 American variants, and Doyle and Gent's list 23 major German variants. This versatility meant that military forces could adapt to changing tactical requirements without developing entirely new vehicles. A factory producing M3 chassis could support artillery, infantry, anti-aircraft, and logistics units, dramatically simplifying the logistics and training burden. The suspension system design proved influential beyond the half-track itself. The vertical volute suspension, refined through half-track development, influenced American tank designs, including the M4 Sherman. The principle of using numerous small road wheels with substantial suspension travel became standard in tracked vehicle design. Modern armored personnel carriers and infantry fighting vehicles, though fully tracked, employ suspension systems that trace their conceptual ancestry to half-track engineering. The open-top design, controversial during development, proved to have unexpected benefits that influenced later designs. The situational awareness it provided was repeatedly cited in after-action reports as tactically valuable. This led to post-war designs like the M113, which, though it could be configured with a closed top, was frequently operated with hatches open to maintain awareness, validating the half-track designer's original compromise.
What failed? Lessons and overcompromise. The half-track's limitations were as instructive as its successes. The vehicle's eventual obsolescence resulted from fundamental engineering compromises that could not be overcome through modification. The hybrid wheeled-tracked system, the half-track's defining feature, proved to be its fundamental limitation. In attempting to combine the advantages of both wheels and tracks, the design inevitably incorporated disadvantages of both. The front wheels, carrying approximately one-third of the vehicle's weight, limited mobility on soft ground. They required complex steering systems that added weight and mechanical complexity. The transition from front wheels to rear tracks created a discontinuity in the vehicle's footprint, affecting handling and creating a tendency for the vehicle to pitch forward when braking on soft ground. Modern mobility analysis using techniques unavailable to 1940s engineers reveals why fully tracked vehicles ultimately proved superior for military applications. A tracked vehicle's continuous footprint distributes weight more evenly than a half-track's divided weight distribution. The lower ground pressure of fully tracked vehicles provides measurably better mobility in soft soil, snow, and mud. While fully tracked vehicles are more mechanically complex, the mobility advantages in military operations proved worth the added complexity. The armor protection compromise also proved ultimately untenable. The half-track's thin armor protected against small arms and shell fragments, but provided no protection against anti-tank weapons. This created a dangerous intermediate category. The vehicle was armored enough to give crews a false sense of security, but not armored enough to survive anti-tank fire. By the late 1940s, military doctrine recognized that armored vehicles needed either true battlefield protection, requiring much heavier armor, or should be unarmored but highly mobile. The half-track's middle ground became a liability. The M113, learning from the half-track. The development of the M113 armored personnel carrier, documented in U.S. Army Tank Automotive Command records from 1956 to 1960, illustrates how half-track experience informed subsequent vehicle design. The M113 abandoned the wheeled tracked hybrid in favor of a fully tracked design. Engineers at FMC Corporation, which developed the M113, explicitly cited half-track mobility limitations as justification for this decision.
The M113's fully tracked layout provided superior mobility across broken terrain while eliminating the maintenance burden of the half-track's complex front steering system. Aluminum armor represented another fundamental departure. The M113's aluminum hull provided better protection than the M3's steel plate while weighing significantly less. This weight savings allowed the M113 to carry more infantry, 11 compared to the M3's 10, while maintaining better mobility. The use of aluminum was made possible by advances in metallurgy and welding technology, unavailable during World War II. But the impetus to seek lighter armor came directly from half-track combat experience. The M113's amphibious capability addressed another half-track limitation. The M3 could ford streams but could not swim. The M113's boat-shaped hull and water-sealed design allowed it to cross rivers and lakes under its own power. This capability proved valuable in Vietnam and subsequent conflicts, validating the doctrinal lesson that infantry fighting vehicles needed maximum mobility across all terrain types. However, the M113 also incorporated features directly derived from half-track experience. The vehicle's modular weapon mounting system, which allowed rapid conversion between machine gun, mortar, and anti-tank weapon configurations, directly followed the half-track's variant philosophy. The rear ramp for rapid dismount was an M3 feature retained in the M113. Even the M113's open-hatch operation doctrine, with crews routinely operating with hatches open for situational awareness, echoed the half-track's open-top philosophy, despite the M113's ability to close its hatches.
Engineering philosophy: the value of imperfect solutions. The half-track's greatest legacy may be philosophical rather than technical. It demonstrated that military engineering often requires accepting imperfect compromises rather than pursuing optimal solutions for specific missions. The half-track was never the best vehicle for any single mission. Trucks were faster on roads, tanks were more mobile cross-country, and purpose-built artillery platforms were more stable. Yet, by being adequate at multiple missions, the half-track provided capabilities that purpose-built vehicles could not match. This philosophy influenced Cold War military vehicle development. The concept of multi-role platforms became central to military procurement. Rather than developing separate vehicles for every mission, military planners increasingly sought platforms that could be configured for multiple roles. The M113 spawned variants serving as command posts, mortar carriers, anti-tank platforms, air defense vehicles, and ambulances, directly following the half-track model. The economic logic was compelling. A single production line producing multi-role chassis could support an entire military force. Maintenance personnel trained on one vehicle type could service an entire fleet. Spare parts inventories could be consolidated rather than fragmented across dozens of vehicle types. These advantages, first recognized during half-track development, became fundamental principles of modern military logistics. Part 6. Technical Deep Dive: Engineering the Impossible. Powertrain engineering: balancing contradictory requirements. The half-track's powertrain presented engineering challenges that required creative solutions to fundamental physical constraints. The white 160AX engine that powered most American half-tracks was a remarkably sophisticated piece of engineering that receives insufficient attention in most military histories. The engine was a 386 cubic inch, 6.3-liter, inline six-cylinder design with overhead valves, an advanced configuration for the early 1940s. Aberdeen Proving Ground testing records revealed the extensive development required to make this engine suitable for military service. The military specification required the engine to operate continuously at full power in ambient temperatures ranging from -40 degrees Fahrenheit to +125 degrees Fahrenheit, a thermal range that would destroy most civilian engines. Engineers achieved this through careful attention to materials and cooling systems. The engine block used a high-nickel iron alloy that maintained strength at high temperatures while remaining ductile at extreme cold. The cooling system was over-designed by civilian standards, with a radiator capacity nearly 50% larger than a comparable civilian truck.
This oversized cooling system was essential because the half-track frequently operated at high power levels in conditions where airflow through the radiator was restricted by mud, dust, or tactical considerations. Crews sometimes blocked radiator intakes to reduce thermal signature. The lubrication system required particular innovation. The engine needed to provide adequate oil pressure immediately on starting in Arctic conditions, while preventing oil breakdown during sustained operation in desert heat. Engineers specified a multigrade oil years before such lubricants became common in civilian vehicles. They also designed an oil cooler system that could be bypassed in cold conditions or engaged in hot conditions, a manually operated system that required crews to monitor oil temperature and adjust accordingly. The transmission presented perhaps more difficult challenges than the engine itself. The 4-speed gearbox with 2-speed transfer case needed to provide smooth shifts under combat conditions while tolerating inexperienced drivers and minimal maintenance. Military transmissions faced demands far exceeding civilian applications. A military driver might shift from first to fourth gear in seconds during a tactical acceleration, imposing shock loads that would destroy a civilian transmission. The same driver might operate in first gear for hours during convoy operations, generating heat that could burn out synchronizers. Spicer Manufacturing Company, which produced most American military transmissions of this era, addressed these challenges through robust design and generous specifications. Gear teeth were cut with larger face widths than civilian practice dictated, spreading loads and reducing wear. Synchronizers were made from phosphor bronze rather than brass, more expensive but far more durable. The transmission case was cast from ductile iron rather than aluminum, accepting a weight penalty in exchange for immunity to impact damage. The transfer case added another layer of complexity. This unit had to split power between front wheels and rear tracks, while allowing the front wheels to be disconnected entirely at high speeds. The engineering challenge was maintaining equal torque distribution between front and rear drive systems despite their different rolling radii and traction characteristics. If the system sent too much power to the front wheels, they would spin uselessly on soft ground. If it sent too much power to the tracks, the front wheels would skid and wear rapidly. The solution employed a viscous coupling, a fluid-filled chamber with interlocking plates that allowed slight speed differences between front and rear drive systems while automatically balancing torque distribution. This was sophisticated technology for the 1940s, representing engineering that wouldn't become common in civilian four-wheel drive vehicles for another 4 decades. The viscous coupling allowed the front wheels and rear tracks to turn at slightly different speeds during turns, while ensuring that power automatically shifted to whichever system had better traction.
Track system engineering, the rubber-steel hybrid. The half-track's track system represents one of the most successful compromises in the entire design. It had to be durable enough to survive thousands of miles of operation, light enough not to impose excessive weight penalties, flexible enough to conform to irregular terrain, and simple enough for field maintenance. The track design that emerged from testing consisted of multiple layers, each serving specific functions. The base was a heavy canvas fabric impregnated with natural rubber, a material choice that seems primitive by modern standards but represented sophisticated materials engineering for the 1940s. The rubber provided flexibility and damping, allowing the track to conform to ground contours and absorb impacts. The canvas provided tensile strength and prevented the rubber from tearing. Embedded within this rubber canvas matrix were steel cables running longitudinally along the track. These cables, typically 3 per track section, bore the primary tensile loads. When the half-track accelerated, pulling forces were transmitted through these steel cables rather than through the rubber, which would have stretched and torn. The cables were positioned precisely within the track cross-section to prevent uneven loading and premature failure. The outer surface of the track featured steel grousers, transverse bars that provided traction. These grousers were not simply bolted on, but were vulcanized into the rubber during manufacturing. The vulcanization process created a molecular bond between steel and rubber far stronger than mechanical fastening could achieve.
Each grouser had a specific profile developed through extensive testing that optimized traction across various terrain types while minimizing track wear on paved roads. Aberdeen Proving Ground testing records revealed the extraordinary development effort invested in perfecting this track design. Engineers tested tracks across sand, mud, snow, gravel, and pavement, measuring wear rates, traction coefficients, and failure modes. They discovered that track life varied enormously with operating conditions. On paved roads, tracks might last 5,000 miles. In abrasive sand, the same track might fail after 1,000 miles. In mud, which seemed less destructive, tracks could fail even more rapidly due to constant flexing and stress cycling. The track tensioning system added another layer of complexity. Tracks had to be maintained at precisely the correct tension. Too loose, and they would throw off the drive sprocket. Too tight, and they would impose excessive loads on the suspension and wear prematurely. The tensioning system used an adjustable idler wheel at the rear of the track assembly. This wheel could be moved forward or backward by turning a large threaded adjustment bolt, increasing or decreasing track tension. Military specifications required that tracks remain properly tensioned across the enormous temperature range the half-track was expected to operate in. But rubber expands and contracts with temperature changes far more than steel does. A track properly tensioned at -20 degrees Fahrenheit would be dangerously loose at +100 degrees Fahrenheit. Engineers addressed this through careful selection of rubber compounds that minimized thermal expansion and by specifying tension adjustment procedures for different temperature ranges. Track life became a logistics concern as critical as fuel consumption. Honeycutt's chronicles note that American forces in Europe consumed tracks at astonishing rates. Units sometimes required complete track replacement every 2,000 miles during intensive operations. This consumption rate drove a massive logistics effort. Track manufacturing facilities operated around the clock, and the military logistics system developed specialized procedures for track distribution, field replacement, and salvage of damaged tracks for rebuilding. Suspension engineering, absorbing the impossible. The half-track suspension system had to reconcile requirements that seemed physically incompatible. It needed to provide enough travel to absorb impacts from cross-country movement at speed, while remaining stable enough to serve as a firing platform for artillery pieces generating 25,000 pounds of recoil force. It needed to support 9 tons of vehicle weight while maintaining ride quality that didn't exhaust crews during long movements. The vertical volute spring suspension that engineers selected represented a significant innovation. Each road wheel was mounted on a trailing arm that pivoted at its forward end. A large coil spring mounted vertically within a tubular housing provided suspension force. As the wheel encountered an obstacle, the trailing arm rotated, compressing the spring. This design provided several advantages over more conventional horizontal spring arrangements. The vertical mounting allowed engineers to use longer springs with more coils, providing greater suspension travel within a compact package. The trailing arm geometry could be precisely calculated to provide progressive spring rates. The suspension became stiffer as it compressed, preventing bottoming even during severe impacts. The vertical arrangement also provided better lateral stability than horizontal springs, reducing body roll during turning. Each track assembly incorporated 4 road wheels with independent suspension, a design choice that seems obvious now, but represented advanced thinking in the early 1940s. Independent suspension allowed each wheel to respond to terrain irregularities without affecting the other wheels. This meant that when one wheel hit a rock, only that wheel's suspension compressed, keeping the vehicle body relatively level and maintaining stability. The engineering calculations for this suspension system were formidable. Engineers had to account for numerous load cases: the static load of the vehicle at rest, the dynamic loads during high-speed road travel, the impact loads during cross-country movement, the asymmetric loads during turning, and the recoil loads during weapons firing. Each load case imposed different force distributions on the suspension components. Spring rate calculations revealed the sophistication of the design. The springs had to be soft enough to provide comfortable ride quality, important because crew fatigue was recognized as a tactical concern, but stiff enough to prevent excessive body motion. Too much body motion would make the vehicle unstable and difficult to control. The springs also had to avoid resonating at frequencies that matched the vehicle's natural vibration modes. If the suspension natural frequency matched the frequency of terrain inputs at typical operating speeds, the vehicle would exhibit violent oscillation that could cause loss of control or mechanical failure. Damping proved as critical as spring rate. Springs alone would allow the suspension to oscillate after encountering a bump, with the vehicle bouncing repeatedly before settling. Damping, friction that dissipates energy, was required to control this oscillation. The half-track suspension used friction damping rather than hydraulic shock absorbers. Friction discs within the spring housing rubbed against each other as the spring compressed and extended, converting kinetic energy into heat and preventing oscillation. The friction damping system was remarkably crude by modern standards, but proved durable and maintainable. Hydraulic shock absorbers, though superior in performance, were prone to seal failure and fluid leakage in dusty conditions. Friction dampers required only periodic lubrication and could be serviced with minimal tools. This maintainability advantage outweighed the performance benefits of hydraulic damping in military service. Ground pressure calculations revealed the suspension's sophistication. The half-track's rear tracks distributed approximately 6 tons of weight across roughly 1,800 square inches of contact area, giving a ground pressure of approximately 4.5 pounds per square inch. This was dramatically lower than the front wheels, which imposed ground pressure exceeding 20 pounds per square inch. This pressure differential meant that the vehicle's mobility was ultimately limited by the front wheels, precisely what combat experience confirmed.
Weapons integration, making artillery mobile. The engineering required to mount weapons on the half-track chassis reveals how far the design had to be stretched beyond its original concept. The M3 chassis, designed to carry 10 infantrymen and their equipment, was being asked to absorb the recoil forces of weapons that normally required being dug into prepared positions. The 75mm gun mounted on the M3 GMC provides an instructive example. The gun generated peak recoil forces exceeding 10,000 pounds, occurring over approximately 0.05 seconds, a violent impulse that the suspension system was never designed to handle. Engineers' solution involved distributing these forces across multiple paths simultaneously. The gun mount itself was a massive steel fabrication that spread load across the entire vehicle floor. 12 large bolts secured the mount to reinforced floor beams that had been added specifically for this variant. These beams distributed forces laterally across the chassis frame. The chassis frame, reinforced with additional cross members, transmitted forces longitudinally to the suspension mounting points. Finally, the suspension absorbed what forces remained, with the entire vehicle recoiling backward and downward as the gun fired. But this wasn't sufficient. Without additional measures, the vehicle would have been pushed backward several feet by each shot, requiring the crew to reposition between shots and making rapid fire impossible. The solution was the ground spade, a large steel blade mounted at the rear that could be lowered to dig into the ground before firing. When lowered, this spade essentially made the vehicle part of the ground itself. As the gun fired, the recoil force was transmitted through the vehicle structure into the ground via the spade, rather than pushing the vehicle backward. Aberdeen Proving Ground testing revealed unexpected complications. The spade worked excellently on soft ground, where it could dig in deeply. On hard surfaces like roads or rocky terrain, the spade couldn't penetrate, and the vehicle would still shift during firing. Engineers addressed this with a more complex procedure. On hard surfaces, the crew would dig a hole for the spade before firing, or they would position the vehicle so the spade rested against a natural obstacle like a rock or berm. The 155mm howitzer mounted on the M12 GMC required even more extreme measures.
This weapon generated recoil forces approaching 25,000 pounds, enough to flip the vehicle if not properly managed. The engineering solution transformed the half-track almost beyond recognition. The entire passenger compartment was removed and replaced with a massive steel superstructure that tied directly into the chassis frame rails. This superstructure was not bolted on, but welded, creating a unitary structure that distributed forces throughout the entire chassis. The gun mounting within this structure used a complex system of recoil buffers and recuperators that absorbed energy over a longer time period, reducing peak forces. Outriggers extended from the sides of the vehicle to prevent rollover. These were not simple legs, but sophisticated structures that had to bear asymmetric loads without failing. If the gun fired at maximum elevation toward the side, the recoil force had both vertical and horizontal components that tried to roll the vehicle. The outriggers, positioned precisely based on center of gravity calculations, prevented this rollover, while remaining light enough that two crew members could deploy them manually. The ground spade on the M12 GMC was a massive fabrication that weighed several hundred pounds. It was positioned so that its center of resistance aligned with the gun's recoil center line. When deployed, the spade had to dig into the ground deeply enough that the soil beneath it wouldn't fail under the recoil load. Soil mechanics calculations determined the required spade area. Too small, and it would sink into soft ground. Too large, and it would be impossibly heavy. Testing revealed problems that calculations couldn't predict. The muzzle blast from the 155mm howitzer was so violent that it damaged equipment stored on the vehicle. The overpressure wave propagating from the gun muzzle could knock down crew members if they were improperly positioned. Blast deflectors had to be designed to redirect these forces away from the crew compartment. Even so, firing the weapon was a brutal experience. Crews reported being temporarily deafened despite ear protection, and the psychological impact of repeatedly experiencing these violent forces affected crew effectiveness.
Armor engineering, the protection compromise. The half-track's armor reveals how engineers attempted to provide meaningful protection within severe weight constraints. The armor had to stop small arms fire and shell fragments without adding so much weight that the vehicle became immobile. This required careful analysis of threat environments and ballistic performance. The M3's armor varied from approximately quarter-inch thick on the sides to half-inch thick on the front plate. These thicknesses seem arbitrary until one examines ballistic testing data. Quarter-inch armor plate, when properly angled, could defeat rifle bullets from standard infantry rifles at typical combat ranges, generally 300 yards or more. It could also stop most shell fragments from artillery bursts at distances beyond 50 yards. The angle of armor plates was as important as their thickness. The M3's front plate was angled at approximately 30 degrees from vertical. This angling increased the effective thickness by forcing bullets to penetrate a longer path through the steel. A half-inch plate angled at 30 degrees presented approximately 0.58 inches of effective thickness to a projectile hitting at 90 degrees to the vehicle's direction of travel. This small increase provided dramatically better protection, the difference between being penetrated by heavy machine gun fire and deflecting it. But the armor was explicitly designed not to protect against dedicated anti-tank weapons. Engineers recognized that providing protection against 37mm anti-tank guns would have required armor exceeding 2 inches thick, adding several tons of weight and transforming the half-track into a light tank. The decision to provide only small arms protection was deliberate and doctrine-driven. Half-tracks were not intended to fight tanks or engage anti-tank weapons. They were supposed to transport infantry to battle and provide fire support against unarmored targets. This decision proved controversial in combat. Crews naturally sought better protection, and field modifications adding additional armor were common. After-action reports from North Africa describe units that welded additional steel plates to their half-tracks, sandbagged the floors for mine protection, and even mounted spare track blocks on the hull sides for added protection. These modifications invariably degraded performance. The added weight reduced mobility and reliability, but crews evidently felt the protection was worth the cost. German armor philosophy differed significantly. The Sd.Kfz.251 used thinner armor, typically 8 to 14.5 millimeters or 0.31 to 0.57 inches, but employed more sophisticated geometry. The hull sides sloped outward at the bottom, providing both better ballistic protection through increased angle and improved stability through a wider stance. The interlocking plate design, though more complex to manufacture, provided better structural rigidity than the M3's bolted plate construction. Ballistic testing at Aberdeen and Kummersdorf, the German equivalent, revealed the limitations of thin armor. Both American and German half-tracks were vulnerable to any weapon larger than a rifle. Heavy machine guns like the German MG42 in 8mm Mauser or the American .50 caliber could penetrate half-track armor at typical combat ranges. The Soviet 14.5mm anti-tank rifle could penetrate from extreme range. Anti-tank rifles and light anti-tank guns rendered half-track armor almost meaningless. This vulnerability drove tactical doctrine. By 1944, experienced units knew that half-tracks had to remain behind cover when under fire from anything heavier than rifles. The vehicles were used for transportation and fire support, but withdrew to covered positions when serious resistance was encountered. This was a significant departure from early war doctrine, which sometimes employed half-tracks in assault roles they couldn't survive. Part 7. The economics of compromise. Manufacturing challenges. Producing thousands of variants. The half-track's role versatility, while tactically valuable, created enormous manufacturing challenges. Each variant required specific tooling, unique parts, and specialized assembly procedures. Coordinating this diversity across multiple manufacturers while maintaining quality and delivery schedules tested the limits of 1940s industrial engineering. Honeckett's research reveals that American half-track production involved 4 primary manufacturers: White Motor, Autocar, Diamond T, and International Harvester. Each company brought its own manufacturing culture and capabilities to the program. White, as the design originator, maintained primary responsibility for engineering changes and coordinated manufacturing standards across all contractors. The production system that evolved was remarkably sophisticated. A central engineering office at White maintained master drawings and specifications for all variants. When a new variant was required, engineers at White would develop the conversion design, specifying which parts changed and which remained common with the baseline chassis. This design package would then be distributed to all manufacturers, who would develop their own detailed manufacturing plans based on their specific facilities and equipment. Parts commonality became a major focus. Engineers maintained extensive lists of components common across variants. The engine, transmission, suspension components, and basic chassis structure remained identical across almost all variants. This commonality meant that manufacturers could build up large stocks of common parts, dramatically simplifying inventory management. It also meant that field maintenance personnel could stock fewer parts while still supporting diverse vehicle fleets. The manufacturing process itself reveals the industrial sophistication of American wartime production. The chassis was built on a moving assembly line similar to automotive practice, but with military-specific modifications. Quality control was far more stringent than automotive standards. Each chassis underwent dimensional inspection to ensure mounting points for weapons and equipment aligned precisely with specifications. Welds were radiographically inspected, a process that involved X-raying welds to detect internal defects invisible to visual inspection. Variant-specific conversion happened after basic chassis production. A baseline M3 chassis would come off the main production line, then be diverted to specialized conversion lines depending on its intended role. An M3 GMC gun motor carriage conversion involved removing the standard passenger compartment, installing reinforced floor structures, mounting the gun and its shield, and installing specialized equipment like ammunition racks and fire control instruments. This modular approach allowed manufacturers to respond rapidly to changing military requirements by adjusting the distribution between variants without retooling the entire production line. Quality control records revealed the challenges of maintaining standards during rapid production expansion. Early production vehicles suffered from numerous problems: welds that cracked under stress, tracks that threw prematurely, and engines that failed after minimal service. Aberdeen Proving Ground maintained teams of engineers who analyzed failures, determined root causes, and issued engineering change orders to correct problems. These changes then had to be incorporated into production vehicles while also being retrofitted to vehicles already in service. The economic efficiency of the half-track production system becomes apparent when compared to German manufacturing. Doyle and Gents document that Sd.Kfz.251 production peaked at approximately 4,200 vehicles annually, compared to American production exceeding 41,000 vehicles. This difference wasn't simply a matter of industrial capacity. The German design's complexity, with its sophisticated suspension and interlocking armor plates, required far more skilled labor and manufacturing time per vehicle than the simpler American design.
Life cycle costs beyond initial production. The true cost of military vehicles extends far beyond manufacturing. Fuel consumption, maintenance requirements, spare parts, and training all contribute to life cycle costs that often exceed initial purchase price. The half-track's economics must be evaluated across this entire life cycle. Fuel consumption was significant. The M3's white 160AX engine, producing 147 horsepower, consumed approximately 0.8 gallons per mile during typical mixed road and cross-country operation. With a 60-gallon fuel tank, operational range was approximately 75 miles before refueling. This consumption rate seems excessive by modern standards, but was typical for 1940s military vehicles. It represented a significant logistics burden. A mechanized division with hundreds of half-tracks required thousands of gallons of fuel daily. Maintenance requirements varied enormously with operating conditions. U.S. Army Ordnance maintenance schedules specified oil changes every 1,000 miles, track tension adjustment every 500 miles, and comprehensive mechanical inspection every 2,500 miles under temperate conditions. These intervals shortened dramatically in harsh environments. In North African desert operations, oil change intervals dropped to 500 miles due to dust ingestion. In Arctic operations, daily engine warm-up procedures and frequent lubrication became necessary to prevent freeze damage. The maintenance hour per operating hour metric reveals the vehicle's true operational cost. Ordnance records indicate that the M3 required approximately 0.3 maintenance hours for each operating hour under ideal conditions. This ratio increased to 0.5 or higher in combat conditions. For comparison, a standard military truck of the era required approximately 0.1 maintenance hours per operating hour. The half-track's increased complexity exacted a real cost in maintenance burden. Spare parts logistics presented unique challenges. The half-track required parts from both the automotive world, engine components, drivetrain parts, and the tracked vehicle world, track sections, suspension components, idler wheels. Military logistics systems had to maintain inventories of both part types, complicating supply chain management. The diversity of variants further complicated parts management. A half-track mechanic might need specific parts for personnel carriers, gun motor carriages, mortar carriers, and anti-aircraft variants, all within the same unit. Training costs represented another significant investment. Drivers required training not just in operation, but in the unique handling characteristics of the half-track. The vehicle steered like a truck, but handled differently due to its tracked rear end. It required different techniques for cross-country movement, different recovery procedures when stuck, and different winter operation procedures than either trucks or tanks.
This specialized training required dedicated instructor personnel and facilities that represented real economic costs. The economic comparison with alternative systems reveals why the half-track remained viable despite these costs. A mechanized infantry division equipped with half-tracks required fewer vehicle types than one equipped with separate wheeled and tracked vehicles. This consolidation simplified maintenance training, reduced spare parts inventory, and allowed more flexible vehicle allocation. These systemic benefits partially offset the half-track's higher per-vehicle costs. Part 8. Human Factors. Designing for Combat Crews. Crew Ergonomics. Fighting from a moving platform. The human factors of half-track design receive less attention than mechanical engineering, but were equally critical to combat effectiveness. Crews had to operate complex equipment while exposed to enemy fire, environmental extremes, and the brutal physical environment of combat. The driver's position reveals the compromises imposed by multiple design requirements. The driver sat on the left side of the vehicle, positioned to provide maximum visibility forward and to the left. His seat was adjustable vertically and fore and aft, critical because drivers ranged from 5 feet 4 inches to over 6 feet tall. The seat cushion was minimal by modern standards, but carefully designed to prevent pressure points during hours of continuous operation. The driving controls were arranged following automotive practice, but with military-specific modifications. The steering wheel was larger than civilian practice, approximately 20 inches in diameter compared to 16 inches in contemporary cars. This larger diameter provided mechanical advantage for steering the heavy front wheels, especially when the vehicle was moving slowly through difficult terrain. The steering required significant physical effort. Power steering was rare in military vehicles of this era, and drivers frequently reported arm and shoulder fatigue after long movements. The instrument panel was simplified compared to civilian vehicles. Military doctrine emphasized simplicity and readability under stress. Gauges were large, with clear markings visible in low light. Red lines on gauges clearly indicated dangerous operating conditions. The most critical gauges, oil pressure, coolant temperature, and fuel level, were positioned directly in front of the driver where they could be monitored constantly. Less critical instruments were positioned peripherally. Visibility was both a strength and weakness. The half-track's relatively high seating position provided excellent forward visibility, critical for navigating cross-country terrain and avoiding obstacles. However, this height also made the driver conspicuous. In combat, drivers often found themselves targeted by enemy small arms fire. The windshield, made of laminated glass, provided some protection but could be penetrated by heavy machine gun fire. Drivers routinely lowered the windshield in combat, accepting reduced visibility in exchange for eliminating a bright surface that attracted fire. The commander's position, typically directly behind the driver, presented different challenges. The commander needed to observe the tactical situation, communicate with the driver and other crew members, and operate the vehicle's primary weapon, typically a .50 caliber machine gun. These tasks couldn't be performed simultaneously. In practice, the commander constantly shifted attention between tasks, relying on other crew members to alert him to threats he might miss while focused elsewhere. The passenger compartment design reflected hard lessons about infantry fighting from vehicles. Early half-track designs had bench seats facing inward, a layout optimized for road movement but disastrous in combat. Infantry facing inward couldn't see threats and were disoriented when the vehicle maneuvered suddenly. Later designs incorporated benches facing forward or outboard, allowing infantry to observe their surroundings and be psychologically prepared for dismount. The dismount process received careful engineering attention. The rear door folded down to form a ramp, allowing rapid exit. Testing at Fort Benning established that a trained squad could fully dismount in under 15 seconds. This rapid dismount was essential. A stationary half-track presented an excellent target, and infantry needed to exit and disperse quickly when combat began. The ramp design was optimized for speed rather than comfort, with infantry essentially running down the ramp and dispersing rather than carefully stepping off.
Sensory environment. noise, vibration, and fatigue. The sensory environment inside a half-track was brutal by any standard. Understanding this environment is critical to comprehending the human challenge of operating these vehicles. Noise levels were extreme. The engine, positioned directly in front of the driver and commander, generated sound levels exceeding 100 decibels during normal operation, equivalent to a chainsaw or jackhammer. At high engine speeds during tactical movements, noise levels approached 110 decibels. The U.S. Army didn't mandate hearing protection in the 1940s, and many half-track crewmen suffered permanent hearing loss during their service. The track noise added another layer of auditory assault. Each track section striking the ground created a sharp impact sound. At road speeds, with the tracks rotating rapidly, this created a continuous roar that made communication nearly impossible. Crews developed hand signals and simple visual communication methods because shouting was often insufficient to be heard over the mechanical cacophony. Vibration created insidious fatigue that affected crew performance. The engine's inline six-cylinder configuration, while mechanically simple, created vibration at frequencies that transmitted efficiently through the vehicle structure. The steering wheel vibrated continuously. Drivers reported numbness in their hands after hours of operation. The seats, despite their careful design, transmitted vertical vibrations that caused back fatigue and reduced crew alertness. The combination of noise and vibration created cognitive fatigue beyond simple physical exhaustion. Studies of sensory environments, though primitive in the 1940s, were beginning to recognize that sustained exposure to high noise and vibration levels impaired decision-making and reaction time. After-action reports occasionally mention crew errors attributed to fatigue, drivers who failed to see obstacles, commanders who missed tactical opportunities, gunners whose accuracy degraded during long engagements. Temperature extremes added to crew stress. In North African operations, interior temperatures routinely exceeded 120 degrees Fahrenheit. Crews suffered heat exhaustion, and the metal surfaces inside the vehicle became hot enough to cause burns on contact. Winter operations presented opposite problems. Interior temperatures could drop below zero, and metal surfaces became painfully cold to touch. The engine provided some heat, but the open passenger compartment offered no protection from wind chill during movement. Dust and fumes created both immediate discomfort and long-term health effects. Desert operations created dust clouds that penetrated every opening in the vehicle. Crews breathed this dust continuously, and many developed respiratory problems. Engine exhaust, containing carbon monoxide and other combustion products, sometimes entered the passenger compartment when the vehicle operated in defilade positions or when wind conditions were unfavorable. Crews occasionally suffered carbon monoxide poisoning severe enough to impair judgment. Psychological factors: fear and fighting from open vehicles. The psychological experience of fighting from an open-topped, lightly armored vehicle created unique stresses. Infantry riding in half-tracks could see threats approaching: incoming artillery rounds, enemy troops, anti-tank weapons preparing to fire. This awareness, while tactically valuable, was psychologically devastating. Combat stress documentation from World War II, though less sophisticated than modern studies, clearly identifies the half-track environment as particularly stressful. Infantry reported feeling exposed and vulnerable, knowing that the armor protecting them was minimal. The sound of bullets striking the hull created intense fear responses even when the armor successfully stopped penetration. Near misses from anti-tank weapons, which might miss or fail to detonate, still generated shock waves and fragments that injured crews without actually penetrating the vehicle. The open top, though providing tactical awareness, created psychological vulnerability. Infantry in closed-top vehicles felt protected, even though armor might be no thicker. The psychological comfort of enclosed space was absent in half-tracks.
Crews were constantly aware of their exposure to artillery airbursts, which could kill through blast and fragmentation without penetrating any armor. This awareness created chronic stress that affected crew effectiveness. Unit cohesion and crew training proved critical to managing these psychological stresses. Experienced crews developed confidence in their vehicles and their own abilities. They learned to distinguish between serious threats requiring immediate response and minor threats that could be ignored. Inexperienced crews, by contrast, sometimes panicked at the first contact with enemy fire, abandoning vehicles that were in fact still functional and safe. The cultural differences between American and German forces affected how crews adapted to half-track combat. American doctrine emphasized individual initiative and vehicle abandonment when situation became untenable. German doctrine emphasized holding position and fighting from the vehicle even under heavy fire. These doctrinal differences reflected different military cultures, but also different vehicle designs. The Sd.Kfz.251's better protection made fighting from the vehicle more survivable than in the more lightly armored M3.
Part 9. Strategic Impact and Tactical Innovation. The Half-Track Division, Mechanized Warfare Doctrine. The half-track's greatest impact may have been enabling an entirely new form of warfare, the mechanized infantry division capable of sustained mobile operations across varied terrain. This doctrinal innovation changed how armies fought and ultimately contributed to Allied victory in World War II. The U.S. Army's armored divisions of 1943 to 1945, as outlined in FM 1742, were built around a close integration of tanks, mechanized infantry in half-tracks, and self-propelled artillery. This integration was possible only because the half-track provided infantry with mobility matching that of tanks. Previous doctrines had separated infantry and armor, with each conducting independent operations and coordinating only at specific phases of battle. The mechanized division fought as an integrated team throughout all phases of combat. The tactical doctrine that emerged was revolutionary. In an attack, tanks would lead, engaging enemy anti-tank weapons and suppressing defensive positions. Half-tracks followed closely, typically within 200 to 300 yards, ready to deploy infantry at critical moments. When tanks encountered obstacles or heavy resistance, infantry would dismount and reduce the position while tanks provided fire support. This integration achieved combined arms effects that neither tanks nor infantry alone could match. The key innovation was speed of response. In previous doctrines, calling forward infantry support might require hours, while trucks transported troops from assembly areas. In mechanized doctrine, infantry was immediately available because they accompanied tanks throughout the advance. This responsiveness allowed armored divisions to maintain momentum, exploiting successes rapidly before defenders could reinforce or reorganize. The pursuit phase of operations demonstrated the mechanized division's unique capabilities. After breaking through enemy defenses, armored divisions could pursue defeated forces at sustained high speed. Half-tracks allowed infantry to keep pace during these pursuits, preventing enemy forces from establishing new defensive lines. The combination of tank firepower and infantry presence made it difficult for defenders to slow the advance through obstacles or rearguard actions. German mechanized doctrine, developed earlier and refined through the Polish and French campaigns, followed similar principles but with different emphasis. German panzer divisions concentrated armored strength in separate tank formations rather than distributing tanks throughout the division. Mechanized infantry and Sd.Kfz.251 half-tracks formed separate panzer-grenadier battalions that fought in coordination with tanks rather than being directly integrated. This doctrinal difference reflected different strategic circumstances. German operations in 1939 to 1942 emphasized breakthrough and exploitation, concentrating armor to shatter enemy lines, then exploiting deep into rear areas. This favored concentrated tank formations, with mechanized infantry following to secure territory.
American operations in 1943 to 1945 emphasized sustained pressure across broad fronts, maintaining continuous contact and preventing enemy reorganization. This favored closer integration of armor and infantry. Innovation under fire, field modifications, and tactical adaptation. Combat experience drove continuous innovation in half-track employment. Units developed field modifications, tactical techniques, and organizational adaptations that their original designers never envisioned.